Okay, anybody can hear me? Okay, okay. Let me start by thanking the organizer for giving me the opportunity to speak here. Basically, I'm going to present the result of my thesis, which I just defended on March of this year, so it is still quite a good exercise for me to present it to any other one else of my advisor. So here is the plan of my speaking. So let's begin with point one. So let's go back to algebra, where the notion of Morita equivalence was born by the hand of Morita. This is like, I think, more or less over there. And the idea of Morita was to identify unital algebras which have equivalent categories of, for example, F module. And don't worry if any of you is not familiar with this notion here. One important thing about Morita's work is that he showed that this notion here is equivalent to the existence of a certain type of bimodule over the algebras A and B, which establishes the equivalence. These bimodules have to be something called balanced. And if you look at each module, like over A and over B, they have to be progenerators. Again, don't worry if you are not familiar with these notions. The point here is that the idea of equivalence he was introducing is established by a certain type of bimodules. And this idea was very fruitful because it allowed you to introduce Morita equivalence almost everywhere when you can define a nice notion of bimodules and certain nice tensor product between them. So one of those instances which is important for us is Poisson geometry. So we are going to choose work in, I think it's 1991. So he considered Poisson manifold, P1, P2, and in this situation, the role of bimodule is played by the so-called symplectic dual pairs. And I will rely on the previous speakers who already introduced this subject here. So I'm going just to repeat verbally here. What's the situation here? You have your two Poisson manifolds, and you have a symplectic manifold which realize both Poisson manifolds. And the main point here is that the fibers of this G1, G2 are symplectic orthogonal here inside. And okay, this is quite too general notion. So to have a good notion of equivalence, we have to refine this definition. And so the equivalence by models will be something with more properties. Like in algebra, we also have some additional property that we ask for the bimodule to be an equivalence bimodule. Here we ask for this symplectic dual pair to be a complete, full, let me call this one, symplectic dual pairs as in one, with additional condition that the Ji fibers being connected and simply connected. So you have all these topological conditions here. You can define a good notion of tensor product between symplectic dual pairs that allow you to show that the relation established between P1 and P2 by this kind of structure is, for example, transitive. Okay, so let me see what else I wanted to say here. So basically that. So symplectic dual pairs with this additional condition, and let me just mention here, complete means that if you have a function here whose Hamiltonian is complete, then its pullback here is a function with complete Hamiltonian too. And full means that these maps are surjective submersion. Some authors actually put all this in the definition of dual pair already to simplify the lives. Okay, so let me picture you here a landscape of Morita equivalence. What you can find more of this in the work of Landsman. As I told you, whenever you have a good notion of bimodule and tensor product between them, you are likely to be able to introduce a notion of Morita equivalence. And that, for example, can be done in groupoids. It can be done in von Neumann algebras. It can be done in C-star algebras. And as we saw here, it can be done in Poisson manifold. And okay, so this is very roughly speaking. For example, in groupoid, you have many subcategories like topological, Lie, symplectic, measure groupoid, and so on. And what Landsman did in this work was to show that many standard constructions that you have to go from groupoid to any of these settings are functorial, but not with respect to the obvious categorical structure in these worlds. What can be done is to introduce a new notion of morphism between the object here by taking as morphism the isomorphism classes of the bimodules that you introduce there. And with that notion of category, this natural construction that was done elsewhere are functorial. And there is one more thing. With those notion of morphisms, with that notion of category, the Morita equivalence in each of these instances boils down to isomorphism between these objects. So what Landsman showed was that these constructions are functorial, and so they preserve Morita equivalence. Let me just tell you how, for example, you come here, which is the one I am familiar with. You take Lie groupoids, you go to its Lie algebroid, and in the dual of the Lie algebroid, you have a natural Poisson structure. So it gives you a Poisson manifold here. And that construction is functorial with respect to those notion of categories. Here you have to use measure groupoid, and here also Lie groupoids, but I'm not familiar with the construction. And so, two questions up to here. How could be the original place where Morita equivalence was born enter into this landscape? This is the first question. And the second question is, why should we even expect that it could be done, something similar to this, involving this universe here, algebra? So let me just put here algebra. And first of all, we do have a way to link this with this universe here. Maybe just this way. And I will write here Kontsevich But there is a detail here. Essentially, you take a Poisson manifold and you have a way to construct a non-commutative algebra associated to it via a procedure done by Kontsevich. But the point is that Kontsevich actually pushed us outside this a little bit, and we have to consider formal Poisson structures. And there is some results scattered over there that indicate that there might be some kind of relationship between Poisson geometry and algebra in terms of Morita equivalence. One of them is the following one. You take M, a manifold. It was shown by Bursztyn and Weinstein around 2004 that if you consider the Picard group of the algebra of function of this manifold, the Picard group is just the group of self-Morita equivalences of this object. This is isomorphic to this group here, the diffeomorphism of M, semi-direct product with this Picard group here. Okay, and on the other side, if you take the Picard group of the manifold M with the zero Poisson structure in here, which is just also the group of self-equivalences of this Poisson manifold, according to the definition of Xu, then this is the diffeomorphism of M in semi-direct product with A2 of M R. So they interpret this as follows. You can in some way see this as a trivial quantization of this zero Poisson structure on M. So they wonder if there could be some more general result that may explain this similarity that you see here, that where this group here seems to appear here in a quantized version, where you only are allowing here integral coefficients or something like that. Okay, so that is basically the motivation. At least it's motivated me to work on my thesis. And with that picture, then let me write here what is our goal. So we want to introduce notion of Morita equivalence of formal Poisson structures and study how it relates with Morita equivalence in algebra. Okay, that's our goal. So, as I told you, we do have a way to take a Poisson manifold and get a non-commutative algebra in this situation through Kontsevich. Let me give a little more detail about that. What Kontsevich did in 1997 was a way to go from this set to this set here. And I am going to describe this set right now. So very quickly, this set here is a set of formal power series of bivector fields on M such that they satisfy formally this equation here, where you take the Schouten bracket and just extend it lambda linearly in this formal power series, and model a notion of equivalence, where you say that pi and pi prime are equivalent if there exists a formal power series of vector fields so these are vector fields on M such that pi prime is the exponential of Lie x applied on pi. And the other set here, def M, is the set of star products. Let me just. Also quotient by an equivalence relation, and a star product on M is nothing but a product in this space, formal power series of function on M this way, which is associative, and it is of the form f star g equal fg plus lambda c1 fg plus lambda square c2 fg plus and so on. So you are asking him to be associative and to deform the commutative original product on C infinity of M. And for geometric purpose, I think, we usually ask to them to be also, to this C1, C2, and so on, to be bidifferential operators. They are so bidifferential operators. Okay, there is many things we can say about this. For example, you can always find a star product which is unital and where the unit is still the unit function, the unit for this undeformed product. And the notion of equivalence here is just an isomorphism so you say that star is equivalent to star prime if there exists an isomorphism of this form. Okay, so it must be a formal power series of maps just because it is linear over the ground field. And where you are asking in addition is that it starts with identity. So then we have those sets. And what Kontsevich gives you is a way to take this here and send into a star product here. But not only that, if you play a little bit with this expression here, using the associativity, you will see that this C1 satisfies the following property. If you take its commutator, it essentially gives you a Poisson bracket on the space of functions. So what this map has is that if you take this star product finds this term in its formal power series expression and do this game here, then you recover the first term in this expression, this one here. Okay. I think that is all I want to say about Kontsevich map for now. So with that, let's go to our definition.
So these T's don't have to be vector fields as before?
No.
They're always the exponential of a vector field. If they start with the identity, they're always the explanation of something that has to be a derivation.
So they do have.
Is that in general? I'm not sure, but
T is the exponential of L of X as written there.
I'm saying that, yeah, what I'm saying is that anything that starts with the identity is the explanation of something. In this form.
So it's a formal diffeomorphism.
Yeah, it's a form.
no, but for that you don't have to ask that this is an automorphism of the underformer product. I think that is. Okay. So let's go to the definition. Okay. So this is part 2 already. Before that. So we want to define a notion of Morita equivalence for formal Poisson structures. So recall Schur's Morita equivalence. What do we have there? We have this symplectic bimodal. I will call it equivalence. Symplectic bimodal. And okay, we can dualize this to get the algebra of functions. Let me just put omega here for the bracket. Call it J1, J2. So you get here J1 pullback, and you get here J2 pullback from say infinity P2 with this bracket. I am not writing here, but these are Poisson algebras. And the condition of these symplectic bimodules gives you here some algebraic properties like G1 pullback is Poisson, and the other one is anti-Poisson. And the fact that the fibers here are symplectic orthogonal is equivalent to the fact that this G1 pullback say infinity of P1 and G2 pullback say infinity P2 are mutually centralizer. Okay, so another comment before writing a definition is that when you have one of these formal Poisson structures, besides getting a star product through Kontsevich map, you get a Poisson bracket on this space, but with the underformed product. Okay, so you can consider say infinity of P lambda with the formal Poisson structure as a Poisson algebra. And so what we will do for our definition is just take these algebraic properties and take this as definition when we have here formal structures. So let's write that here. So this is our definition. You have P1, Pi1, and P2, Pi2 formal Poisson. Then they are Morita equivalent if two conditions are satisfied. The first is that there exists a symplectic manifold and a diagram like this. Where or with omega, this here being something like omega 0, this symplectic structure here, deformed by closed two forms. So this belongs to omega 2 closed of the manifold S, formal power series. And Phi1 you ask to be Poisson, Phi2 to be anti-Poisson. And these algebras of function, when you look at them inside through the maps, they must be mutually centralized. So this and Phi2, same infinity of P2 lambda, are mutually centralized. So there is a second condition, but before going to that condition, just some comments here. This structure here starts with a symplectic form. So the formal power series is formally invertible. And you can check that the inverse of this gives you a formal Poisson structure, which induces the Poisson algebra here, with respect to which you are saying that these maps are Poisson. Okay, so
You asking that Phi1 and Phi2 be injected?
yeah. They will be particular for the second condition. Let me just write the second condition here. The second condition is that in the classical limit, we just mean put lambda to 0 everywhere. You get this the zeroth order term of this formal Poisson structure is an ordinary Poisson structure. You get here a map G1, you have your symplectic manifold, and you have here other map, and here you have P2 with the zeroth order term of Pi2. This has to be a Schuss-Morita equivalence. So this map comes from this one here, or we want to be related with this map as follows. These are formal maps as follows. This is Phi1 0 plus lambda something. This is Phi2 0 plus lambda something. So for this to be Poisson, it has to be a homomorphism of the underformal product here. So this first term has to be a homomorphism. So it must be a pullback of some map. And for this to be Morita equivalence, this has to be subject to submersion which implies that this has to be injective, and so on. So,
Oh, one thing, when you define formal Poisson structures, they started with the term one.
yes, that is.
But now you're allowing more.
Yes, that's the point. This definition is a little more general than what we are going to consider for our main result. Here we are allowing the zeroth order to be non-zero. And that is a more general situation for which we have actually open questions. And the main result is going to be concerned with the case that the zeroth order term is zero here. Okay, how much do I have? 10? 12, okay. Okay, so at least we have all the definition to state the main result. Yeah, I can say that right here. So, main result, we can say as follows. Basically, Morita equivalence in this set, and here I am taking the domain of the Kontsevich map. Particularly, I am taking the zeroth order term to be zero. This is the same as another notion of equivalence in this set, which is gauge or B-field equivalence. So, for people who are not familiar with this, let me introduce you this notion. So I will write again here the diagram of Kontsevich map. This V-field equivalence is an equivalence here given by an action of this group here. And the action is as follows. I will call it tau. So you take an equivalence class here, and you take your equivalence class here, and you map this to something denoted this way, where this new formal Poisson structure is characterized by this associated map, which you just define as follows. So this is inspired by the same transformation that you can do in the undeformed situation, only that there you have to take care about this map here being invertible. Here in the formal case, working in this domain, the fact that this pi star at order lambda guarantees that this is always invertible. So at least this is well defined. And you can play around with this to show that this actual action and the action descends to the equivalent classes. And, okay, so we do have this notion of equivalence here. And the main result that we found is that our definition of Morita equivalence, when you restrict to this setting, is the same as this gauge equivalence. I have to put here up to action of the group of diffeomorphism. This is going to appear everywhere, so any equality is always up to this. And what is the good about this situation? We can improve this diagram. There is also an action here. All this diagram that I'm going to draw here came from a series of papers involving Bursztyn, Dolgushev, Stefan Baldman. And the final picture is as follows. You have here an action of the picker group. This picker group is not the picker group of self-equivalences of Morita, self-Morita equivalences. This is isomorphic to A2MC via the Chern map. This is the group of isomorphism classes of complex light bundles over M. And this acts on the formation, and more, it classifies Morita equivalent star products. So, there is more about it. It classifies Morita equivalent star product, and this map here is a equivariant between these two actions under some condition. If you take this L here, the isomorphism class of a complex line bundle, this gives you this close to form, I think something like this, where this is a Chern map, or first Chern map. And with that be filled, this is equivariant. It means you take phi L of the Kontsevich map, apply it to this equivalence class of formal Poisson structure is the same as taking the Kontsevich map of the equivalence class of this formal Poisson structure. So we can summarize in the following diagram. We have here B-field equivalence in formal in this set. So by this result here, under integrality condition, we have Morita equivalence of star product and our main result is here Morita equivalence in this set. And if and only if with this notion of equivalence. Okay, so I underlined this because I didn't know if we're going to have time. Do I have some time? 5 minutes. Okay, so there are lots of open questions, but let me just point to one. This is not an open question related to this work itself. It is a question about how it may be related to another constructions doing elsewhere. So very, very roughly speaking, there is a series of papers of Karabekov concerning something that he called formal symplectic groupoids. And the outcome of this work is that if you take M, manifold, and a star product, then he constructs what he calls a symplectic, a formal symplectic groupoid. Which is pretty much in the spirit, I erased it, but he constructs this as a structure on the algebra function also associated to an initial symplectic realization. And he dualized everything and construct the analogs of the action of groupoid and check that you can, once you have this star product, you can construct the structure there, which is everything in the space of algebra functions. And for this main result, we did, as a first step, a classifying map, which was something like you have this so so to construct this map here, which we call this way, and then we show that this is actually the same as gauge equivalence. We studied a deformation problem, but going over that, the final product here is that you take M, you take this pi here, and you can construct something that I call a formal dual pair. In particular, you can take b equals 0. So you get something like, here you get your formal Poisson structure. Here you take the cotangent space with the canonical symplectic structure. And here you take your infinity of M, like the self-equivalence of this formal Poisson structure. But then we have Kontsevich map going from here to here. So that curiosity just came to me after I have been discussing with Alejandro a few times after I presented my thesis. And I still don't have any idea of how exactly there may be related this object with this object, but it's something that is out there. And if anyone is also interested in that, you may write me, we may discuss. And I think I will stop there.